Hey everybody, welcome back to Chapter 5, Section 1, Part 2. This is called the Circumcenter and the Incenter. So I have some definitions to go over with you, like what does it mean to be a circumcenter and an incenter? Well, when three or more lines intersect at a common point, the lines are called concurrent lines. The point where concurrent lines intersect is called the point of concurrency. Why is that relevant? Well, a triangle has three sides, so it also has three perpendicular bisectors, which are concurrent lines. The point of concurrency of the perpendicular bisectors is called the circumcenter of the triangle. So again, to just kind of like quickly sum it up, lines A, B, and C are concurrent at point P. That's where they all meet or intersect. And so here you have the circumcenter of a triangle. So these are all perpendicular bisectors. We're talking about PD, PE, and PF. And then if you were to draw additional lines from those to the vertexes or the corners of the triangle, you can create these mini little triangles. But yeah, so the details to remember in this is that when you have a circumcenter, it creates all of these, it's a perpendicular bisector, right? So that means the segments that it bisects will be congruent. So BF is congruent to FC, AE is congruent to EC, AD is congruent to DB. And so also, the segments that you can draw to the circumcenter from the vertex, so PA, PB, PC, those are also congruent to one another. So I could zoom in on this and I'll mark all these as congruent. And so these segments here are all congruent to one another, making these three red lines the only thing that's really different. Now, these lines, like BC, might not be congruent to AC or AB. That's why they're marked with a different number of dashes. Okay, all you know is that they've been bisected, creating two smaller congruent segments. So the circumcenter can be on the interior, exterior, or side of a triangle. It'll be on the inside if we're talking about an acute triangle. That means the biggest angle is less than 90 degrees. It'll be on the exterior if we're talking about an obtuse triangle where the greatest angle is greater than 90 degrees. And then it'll be on the side of a triangle when the circumcenter is in or on a right triangle. So here in this example, we have point D as our point of concurrency or our circumcenter, and it's on the exterior of the triangle, meaning this is an obtuse triangle. So it might be kind of confusing to see, but we're looking at triangle ABC, and so point D is actually on the outside of that. So I'm going to answer some questions. We're going to identify which segments are congruent to each other given that point D is the circumcenter. So the first thing we're going to go over is what is AD congruent to, and that would be DC. It would skip over DE because that's where the perpendicular line is, or the perpendicular bisector is. So, but it needs to be connected by point D, and it needs to go to a vertice. So that means AD will be congruent to DC because they're both meeting at the circumcenter, and then their lines are going to the vertice or the corner of the triangle. And that also means that DB is congruent to AD and CD. So next we'll look at what segments are congruent to AH. And so AH is the picture is real confusing. It's from here to here. So you can see there's a little line going right there. So the segment congruent to AH would be HB because they are on the same side of the big triangle ABC. And so since we're talking about the side of the triangle, that's all we know. We don't know if any of these other sides like CF and FB or EC and AE are also congruent to it. So next we'll look at BF and see what's congruent to BF. So BF is a leg of the triangle, so I'm going to mark that. And so the other segment of that leg of the triangle will also be congruent. So we'll say CF or FC. The order doesn't really matter, but I'll just keep it alphabetical and say CF. Lastly, we'll look at DC. So DC is a vertice, or it's going from the circumcenter to a vertex of the triangle. So in talking about AD, I also answered this question. So what's congruent to DC, AD, and DB? So next we'll talk about the incenter, and the incenter is the point of concurrency when you have angle bisectors coming from the vertices of your triangle. So it's somewhat the opposite of the circumcenter, because if you have these angle bisectors all meeting at the incenter, then it creates congruent segments where it makes the perpendicular segments. So if you draw segments that are perpendicular from point P, the incenter, they will all be congruent to each other. So what I'm trying to say is DP will be congruent to PF, and that'll be congruent to PE. And then you also know that all these little angles, they've been bisected. You don't know if they're congruent to any of the other angles, like angle C, if it's congruent to angle A or B. But what you do know is that the bisected angles, you've created congruent adjacent angles. And one thing that the textbook did not mention in their little example here is that the sides that are opposite from the congruent angles, meaning EC, that's going to be congruent to FC. And the side like BF, that's going to be congruent to like BD. And then like AE, 1, 2, 3, 4, will be congruent to AD, 1, 2, 3, 4. So it's not quite the same as the circumcenter, because the circumcenter said AE is congruent to EC. But if you look at it, the sides that, like I said, the sides that are opposite from your congruent, like bisected angles, they are congruent to one another. So in these two examples, we're going to use the properties of the incenter to figure out the missing sides and the missing angle. And so I wrote, hint, we're going to have to use the Pythagorean theorem. So to figure out JF, let's look at what we know. We know that this side is 15, and we know that this side is 12. So using what we know about incenters, we know that these angles are congruent, so that's also 34. This is also 32. And we don't know this angle, but we know that it's congruent to that as well. Also, the segments that extend from the incenter to the side, so not to the vertice, but to the sides, so like JE, JF, and JD, those are all congruent to one another. So if we're looking for JF, we know that this is 15, and that'll be the hypotenuse leg of this triangle, because you have a right angle right here, so then you can conclude that you have a right angle right there as well. And then if you'll recall, I said that the segments that are opposite of one another from their bisected angle are also congruent. So that means that if EA is 12, FA is 12. And so basically we have this right angle triangle here where 15 is your hypotenuse leg, and then 12 is, I guess, the bottom of it. And so we just don't know what this is. So if we do Pythagorean theorem, we can set x squared plus 12 squared and equal that to 15 squared. And if you'll recall, when we talked about the Pythagorean theorem, we talked about Pythagorean triples, you know, where all three sides of the triangle are whole numbers, and the most basic of them being a 3, 4, 5 triangle. And if you multiply 4 times 3, you get 12, and if you multiply 5 times 3, you get 15. So that would mean this side is 3 times 3, which is 9. So if you don't pick up on that, it's okay. I'll show the math right now, showing you that the answer will be 9. But yeah, just thought I should point that out. So when you square the two sides that you know, 12 squared gets you 144, 15 squared gets you 225. You'll want to subtract 144 to the other side. And 225 minus 144 is 81. So you get x squared equal to 81. So you'll want to square root both sides. And the square root of 81 is 9, giving you a side length of 9, like I said would happen. And so JF equals 9. So example 2 says, what's the measure of angle JAC? So we're going to look at JAC right here. And so here's J, and the incenter, and so JAC is this angle right there, and it's actually the angle we do not know. We know this is 32, so that's 32. We know this is 34, so that's 34. But if you look at the big triangle of ABC, then you can subtract the angles from 180. So I'll do 32 plus 32, that's 64. And I'll do 34 plus 34, that's 68. And I'll do 180 minus 64 and 68. And I'll have my answer for angle A. And then I'll just cut that in half to figure out what JAC is. So 180 minus 64 minus 68 is going to get me 48 degrees. So that's what angle A is. Again, so we're going to have to bisect it. So we're going to cut 48 in half, and we're going to get 24 degrees. So that's what angle JAC is. The big angle A would be 48, and the bisected angle of JAC would be 24 degrees. So that's pretty much it for that one. In the next example, I have point P as the incenter of triangle AEC. So I'll find each angle measure or side measure. So it's looking for PB. So PB is this little measure right here. And so you have 13 here and 10.9 there. 13 being the hypotenuse if you were to redraw the triangle. And so we're going to do pretty much what we just did for the previous problem. You're going to go x squared plus 10.9 squared equals 13 squared. And this is not going to be a Pythagorean triple because all Pythagorean triples are whole numbers, and this already has a decimal in it. So that's going to give me x squared plus 118.81 equal to 13 squared is 169. And so I'll minus 118.81 to the other side. And then I will square root that answer. So 169 minus 118.81 is 50.91. So when I take the square root of that, I'm going to get about 7.084, and that is what PB is going to be. The next side it's looking for is DE, and so we know that DE is the same thing as FE, but FE is not labeled, so that doesn't really help us. What we do know is that PB was 7.084, right? And then, so if PB is 7.084, then FP is 7.084, and DP, or PD, is 7.084. So that means we know two of the three sides of a right triangle, so we can use Pythagorean theorem again to figure out what DE is. 14.9 is opposite of the right angle here, so that's going to be my hypotenuse. So I'll do DE as x squared or y squared. It doesn't really matter. I guess I'll do y. I'll call it y for this one because I called the other one x. So yeah, I'll do y squared plus 7.084 squared equals 14.9 squared. So for the 7.084 squared, I guess, typically once you round an answer, you use that rounded answer. I don't know if that's an official thing or not, but since we rounded this from 50.91, if you were to square this rounded number, you get 50.18, so that's kind of close to 50.91, but knowing that x squared equals 50.91 here, I'm just going to use 50.91 rather than using that rounded number. So I hope that makes sense. All I'm trying to do is get a slightly more accurate number. The less you round, the better. So 50.91 is not a rounded number, whereas 7.084 is a rounded number. And 14.9 squared is 222.01. So then I'll want to subtract 50.91 from both sides. And so I can bring down the y squared, and that's going to equal 171.1. And then you'll need to take the square root of both sides. And the square root of 171.1 is approximately, rounding to the nearest thousandths place, is going to be approximately 13.081. It officially says 0.0805, so that 5 will round up that 0 after the 8 to a 1. So yeah, this is what DE is going to equal. Again, I'm hoping I'm not confusing anyone, but if I had used the rounded amount 7.084 squared and not used the 50.91 that I had from earlier, and if I had literally used the rounded number 7.084 squared, I would have gotten a different answer, something close to 13, but I would have gotten a different number, just letting you know. The next blank is much less work. It says, what's the measure of angle DAC? If you look at DAC, it is talking about this angle right here. So if this is 33, then that's 33. And the last blank says, what's the measure of angle DEP? So we look at DEP, and so DEP is right here. So we do not know these two angles, but basically we know that this is 28.5, and so this will be 28.5. So that means if you double 28.5, you get 57. So this is 57, 33, and this is 33. You get 66. So you'll do 180 minus 66 minus 57, and then cut it in half. So doing 180 minus 57 minus 66 is going to give me 57 again. And so when you cut 57 in half, you'll get 28.5. So that's what the measure of angle DEP is going to equal. You could have also done this. Let me write down 28.5. What you could have also done is, since all these angles here are bisected, that means they're all cut in half. So what's 180 cut in half? 90. So what you could have done is you could have done 90 minus 33 and minus 28.5, and you would have gotten 28.5. So that's just another way of approaching this. I just kind of like to reiterate that, hey, all the angles in a triangle add up to 180, and so kids seem to understand it better that way. But the same thing with this one before. If I had done 90 minus 34 and minus 32, I would have gotten 24. So again, you could do that because all the angles in that triangle were bisected. If they weren't all bisected, then you couldn't equal it to 90 like that. But I hope that helps, and thank you for watching, and goodbye.